Tonight, we're going to talk about things in the universe that should not exist, not theoretical things, not science fiction. Real objects out there in space right now that, according to everything we know about physics, simply cannot be there. And yet they are. Some of them are too big. Some of them are too old. Some of them are too massive for their age. Some of them are arranged in patterns that defy what the universe is supposed to look like at its largest scales. And every single one of them is forcing astronomers to admit that something about our understanding of the cosmos is incomplete. I'm not talking about little discrepancies. I'm not talking about minor adjustments to our models. I'm talking about objects so far outside the rules that physicists have written entire papers titled things like "This should not be possible" and "We have no current explanation." Real titles, real papers, real confusion. You might think that after 100 years of modern cosmology, after Hubble and Einstein and decades of space telescopes and increasingly precise measurements, we'd have a pretty solid handle on what's possible in the universe. We've got the standard model of cosmology. We know the universe is about 13.8 billion years old. We know roughly how galaxies form, how stars live and die, how black holes grow. We've got rules. We've got equations. We've got numbers that work. And then the universe shows us something that breaks those rules entirely, not bends them, breaks them. And we sit there staring at the data and asking each other the same question: how is this possible? By the end of this video, you're going to know about 10 of the most impossible objects astronomers have ever found. Some of them are recent discoveries from the James Webb Space Telescope, things we didn't even know existed 5 years ago. Some of them have been puzzling scientists for decades. Some of them are so big the human mind genuinely cannot picture them. And some of them are so strange that the leading scientific explanation is essentially, we don't know, but here are 5 guesses. These aren't just curiosities. These objects are the universe's way of telling us that our picture of cosmic reality is incomplete. That somewhere in our models, there's a missing piece. Maybe several missing pieces. And the only way to find those pieces is to keep staring at these impossible things and trying to understand why they exist when they shouldn't. So get comfortable. Lie back. Close your eyes if you want. Let the strangeness of the cosmos wash over you. Because we're about to descend into some of the deepest, weirdest, most rule-breaking objects ever discovered. And by the time we're done, your sense of what's possible in the universe is going to be very different. Before we dive in, if you find this kind of deep exploration interesting, a like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's start with something that should not be there. Something that's so far out of place in the universe's timeline that the moment we found it, astronomers started questioning whether their entire model of cosmic history was wrong. Let me tell you about galaxies that grew up too fast. In December of 2021, NASA launched the James Webb Space Telescope. It was the most expensive scientific instrument ever built, $10 billion. Decades of development, the successor to Hubble, and the moment it started sending back data, it broke our understanding of the early universe. To explain why, we need to back up a little. The universe is about 13.8 billion years old. We know this from multiple independent measurements. The cosmic microwave background, the expansion rate of the universe, the ages of the oldest star clusters. They all converge on the same answer. The Big Bang happened about 13.8 billion years ago. And everything we see today, every galaxy, every star, every planet, every atom came from that moment. Right after the Big Bang, the universe was a hot, dense soup of particles. There were no stars. There were no galaxies. There were no atoms in any meaningful sense, just a plasma of protons and electrons and photons all bouncing off each other in a glowing fog. This lasted for about 380,000 years. Then the universe cooled enough that the particles could combine into actual atoms, mostly hydrogen and helium, and the fog cleared. Light could finally travel through space without immediately scattering. This is the moment we see in the cosmic microwave background. The afterglow of the Big Bang, the earliest light in the universe. After that came what astronomers call the Dark Ages. The universe was filled with neutral hydrogen gas, but there were no stars yet, no light sources, just darkness. This dark age lasted somewhere between 100 million and 300 million years. Then, slowly, gravity started pulling clumps of hydrogen together. The clumps got denser, they got hotter, and eventually, somewhere around 200 to 300 million years after the Big Bang, the very first stars ignited. These were the first generation of stars in the universe, and they were nothing like stars today. They were massive, they were hot, they burned through their fuel fast and died in spectacular supernovas, scattering the first heavy elements across space. After that, more stars formed. They clumped together. They formed the first proto-galaxies, small, irregular collections of stars and gas. Over hundreds of millions of years, these proto-galaxies merged and grew. They became real galaxies. By about 1 billion years after the Big Bang, the universe had matured enough that fully formed galaxies existed in significant numbers. That's the standard timeline. That's what every textbook says. That's what every simulation predicts. Galaxies need time to form. They need stars to be born. They need gas to clump together. They need supernovas to enrich the surrounding space with heavy elements. They need mergers to grow. All of this takes hundreds of millions of years at minimum. Then James Webb turned on, looked into the deepest, earliest universe it could see, and found galaxies our timeline says couldn't be there yet. One of the early discoveries that really made people sit up was a galaxy designated Mais's galaxy. Webb spotted it in 2022, and follow-up spectroscopy in 2023 confirmed that we were looking at a galaxy that had existed when the universe was only about 390 million years old. That's already extraordinarily early. The galaxy was named after the daughter of one of the astronomers who discovered it, and it was bigger and brighter than models predicted galaxies could be at that age. Then came another one, Jade's GS Z130. This galaxy is even more extreme. We're seeing it as it existed when the universe was only about 320 million years old. The galaxy is small by modern standards, only a few hundred million solar masses, but it's already shining with the light of millions of stars at a moment when the universe should barely be making them. It's been spectroscopically confirmed, which means we know its distance for certain, and it's there, bright, fully formed enough to detect from across the entire universe. Then there's ZFUDS 7329. This galaxy is at a different distance, about 2 billion years after the Big Bang. But what makes it remarkable is its composition. The stars inside it are old, really old. The light from those stars suggests they formed when the universe was only 600 to 900 million years old, then matured rapidly in this galaxy. By the time we're seeing them, they're already a billion years old, glowing with the warm red light of mature stellar populations. This galaxy also has another problem. It's not just full of old stars. It's already done forming new ones. It's what astronomers call a quiescent galaxy. It's quiet. Star formation has stopped. This usually happens to galaxies after billions of years of evolution. The gas runs out, The galaxy can no longer form new stars. It coasts along on its existing stellar population until those stars die. For a galaxy this massive, around 400 billion solar masses, to have formed its stars in the very early universe and then completely shut off star formation while still being relatively young, contradicts our standard models of how massive galaxies grow. The math is hard to make work. And these aren't the only ones. Webb has found dozens of these too mature, too massive galaxies in the early universe. They keep showing up. Every time astronomers analyze a new batch of Webb data, more of them appear. There's a researcher at Royal Observatory Edinburgh named Mike Boylan-Colchin who's been working on this problem. He published a paper essentially saying that if these early galaxies are real, our standard model of cosmology might need significant revision. He's not the only one. Multiple research teams have run the numbers and concluded the same thing. Either the galaxies aren't really as old or as massive as we think, or our understanding of the early universe is wrong. Both of those options are uncomfortable. The first means our measurements are off by enough that the conclusions change. The second means physics has a problem. There are several proposed explanations, and none of them are completely satisfying. One idea is that the very first stars were much more massive than current models predict. If the early universe formed enormous stars, hundreds or even thousands of times the mass of the Sun, then individual stars would have been much brighter, and a relatively small number of them could account for the brightness we're seeing in these early galaxies. The galaxies wouldn't actually be as massive as they look. They'd just be lit up by monster stars that don't exist anymore. This idea has some support, but it has problems too. Where did all that gas come from? How did it form such big stars? And we don't see direct evidence of those monster stars. Another idea is that black holes formed earlier and grew faster than we thought. If supermassive black holes existed in the very early universe, they could power bright sources of light called active galactic nuclei. The galaxies we're seeing might be smaller than they appear, but they have these incredibly bright, black hole-powered cores, making them look bigger and more massive. This explanation has gained traction, but it just pushes the problem back. How did those black holes form so quickly? A third idea is more radical. Maybe our model of cosmology is wrong. Maybe dark matter doesn't behave the way we think it does. Maybe the rate of structure formation in the early universe was different from what our simulations predict. Maybe there's new physics we haven't discovered. A fourth possibility is that we're misinterpreting the data. Webb is the most sensitive infrared telescope ever built, but it's still detecting these galaxies at the absolute limit of its capabilities. Maybe the redshifts are wrong. Maybe we're seeing closer galaxies that look like distant ones because of dust or other complications. Astronomers are working hard to confirm or rule out this possibility. But here's the thing. Even after years of careful analysis, after follow-up observations, after multiple teams independently checking the work, the overdeveloped early galaxies are they're not going away. The universe at its earliest moments had structures we don't know how to build with our current physics. Imagine that. The universe is showing us something that doesn't match a single one of our models. And it's not one or two anomalies. It's an entire population of objects that don't fit. The deeper Webb looks, the more it finds. The earlier we see, the stranger it gets. Let me put this in human terms for a moment. Imagine that you're a detective and you're trying to figure out how someone got rich. You've studied wealth your whole career. You know the rules. People earn money over time. They invest. They compound. They build wealth slowly, decade by decade. The richest people you've ever met spent their entire lives accumulating their fortunes. Then one day you meet a 6-month-old baby with the net worth of a billionaire. The baby has investments, real estate, stock portfolios. The wealth is real and verifiable. Other 6-month-old babies near this one also have similar fortunes. You check your records. The babies are definitely 6 months old. The wealth is definitely real. But there's no time in their lives during which they could have accumulated it. They were born, and immediately, somehow, they had it. That's roughly what astronomers are dealing with when they look at these early galaxies. They've spent careers building models of how galaxies grow. The models work for galaxies in the modern universe. They predict that galaxies grow slowly, accumulating mass over billions of years. And then Webb shows them galaxies the size of the Milky Way that grew up almost as soon as the universe was old enough to have stars at all. Something is wrong, either with our understanding of how galaxies grow, or with our understanding of when stars first formed, or with our understanding of how mass accumulates in the early universe, or with all of the above. We don't know which. We just know the gap exists, and it's getting bigger every year as Webb collects more data. There's another wrinkle that makes this even stranger. Some of these early galaxies aren't just massive. They're already structured. They have shapes that suggest they've been organized into disks and bulges. Modern spiral galaxies have clear structure, with rotating disks and central bulges and spiral arms. We know how these structures form. They take time. They require gas to settle into a disk. They require gravitational interactions over many rotations of the galaxy. Building a structured spiral galaxy takes billions of years. Some of these early galaxies are already showing structure that takes billions of years to develop in our standard models. Disks, coherent rotation, apparent spiral patterns, as if they had skipped the messy formation phase entirely and arrived already mature. This isn't every Webb observation, of course. Many early galaxies do look messy and irregular, the way our models predict. But enough of them look unexpectedly mature that astronomers can't dismiss it as a one-off. Somewhere in the data Webb is collecting right now, there are probably galaxies even more extreme than the ones we've already found. Galaxies that formed even earlier. Galaxies even more massive than they should be. The next few years of Webb observations are going to keep pushing this mystery, and at some point, our understanding of the early universe is going to have to change to accommodate what we're seeing. What's strange, what's almost beautiful about this, is that we built the most expensive telescope in human history, pointed it at the deepest reaches of the cosmos, and the universe responded by showing us something we couldn't explain. We came looking for confirmation of our theories, and we got mystery instead. That's how science actually works. You think you understand something, you build a better instrument to confirm it, and the universe surprises you. The James Webb Space Telescope was supposed to verify the standard model of how galaxies formed. Instead, it's challenging that model, and astronomers are scrambling to figure out what it all means. These galaxies are out there right now. The light from them has been traveling toward us for over 13 billion years. Photons that started their journey when the universe was barely born, finally arriving at our telescope, carrying information that doesn't fit our story, and we don't know why. That's the first object on our list. Not a single object, but a whole class of them. Galaxies that existed too early, grew too big, matured too fast. Galaxies that arrived in the universe before our models say they could have. Let's keep going. Because the next mystery isn't a galaxy. It's a single star, and it might be older than the universe itself. About 190 light-years from Earth, in the constellation Libra, there's a star you can see with binoculars on a clear night if you know exactly where to look. Its official catalog name is HD 140283, but astronomers call it the Methusela star, named after the biblical figure who supposedly lived to be 969 years old. The nickname is appropriate, because by every measurement we have, the Methusela star is the oldest individual star astronomers have ever directly studied. And, depending on which measurements you trust, it might actually be older than the universe. Let me say that again. We have measurements suggesting that an object inside the universe is older than the universe itself. You don't need to be a cosmologist to recognize that's a problem. Here's how we got here. Astronomers can estimate the age of a star using several different methods. They can look at its composition. They can measure its temperature and brightness. They can compare it to models of how stars evolve over time. Different techniques give different answers, and the uncertainties are real. But for most stars, they all agree closely enough to give a reliable age. When astronomers first applied these techniques to the Methusela star in the 1990s, they got a result that everyone assumed must be wrong. The star appeared to be about 16 billion years old. The universe is only about 13.8 billion years old. So either the star measurement was off, or the universe measurement was off, or both. Something had to give. Over the next 2 decades, scientists refined their measurements. They made better observations. They built better stellar evolution models. They used the Hubble Space Telescope to get a more precise distance to the star, which is critical for calculating its luminosity and therefore its age. And as the measurements got more precise, the age estimate kept changing. It came down from 16 billion years to 15, from 15 to 14. By 2013, when a team led by Howard Bond at Pennsylvania State University did the most careful analysis to date, the Methusela star came in at about 14.5 billion years old, with an uncertainty of about 800 million years. That's still older than the universe. But the uncertainty is large enough that it could technically be just barely younger. If the true age is at the low end of the error bars, the star might be about 13.7 billion years old, which would make it just barely younger than the universe at 13.8. That's incredibly tight. There's almost no room. The star, if these measurements are right, formed essentially at the very beginning of the universe. Within the first 100 million years or so, before galaxies were really galaxies. Before the universe had cooled enough for stars like the Sun to be common, the Methusela star would have to be a member of one of the very first generations of stars in cosmic history. But here's the second problem. The Methusela star isn't a first-generation star. We know this because of its composition. The very first stars in the universe were made entirely of hydrogen and helium. There were no heavier elements yet, because heavier elements are made inside stars and scattered when stars die. The first stars had nothing but the primordial elements left over from the Big Bang. The Methusela star has heavier elements. Not many. About 250 times less iron than the Sun, which is extremely low. But it's not zero. The star has been enriched with material from earlier generations of stars, which means it can't be a first-generation star. It has to be at least a second-generation star, formed from gas that had already been enriched by the deaths of even earlier stars. But if it's second generation, it can't be as old as the universe, because the first generation had to live, die, and scatter their material before the second generation could form. That process takes time, probably at least a few 100 million years. So we have a star that by stellar evolution models looks like it's around 14.5 billion years old, but that's older than the universe. And even if the age is at the low end of its error bars, the star can't be much younger than 13.5 billion years old because of its composition. and that gives it almost no time at all to form between the very beginning of the universe and the moment it appeared. It doesn't add up. Astronomers have proposed several ways to resolve this. The most popular is that some of the measurements have unidentified errors. Stellar evolution models have lots of moving parts. The way the star burns its fuel, the way energy is transported through its layers, the way it loses mass over time. Small errors in any of these can compound into bigger errors in age estimates. In particular, low metallicity stars like Methusela are hard to model. Most of our stellar evolution models are calibrated using stars that are more like the Sun, with normal metal content. When you push the models out to extreme low metallicity, they're less reliable. There might be physical processes happening inside the Methusela star that we don't fully understand, processes that affect how quickly it burns its fuel, and therefore how we estimate its age. Another possibility is that our distance to the star is slightly off. The age estimate depends on knowing the star's true brightness, which requires knowing its distance. The Hubble Space Telescope measured the distance directly using parallax, which is the gold standard for distance measurements. But there's still some uncertainty. If the star is slightly closer than we think, it would be intrinsically dimmer, which would mean it's not as old as we calculated. The Gaia satellite, launched in 2013, has been measuring the positions and distances of over 1 billion stars with unprecedented precision, including the Methusela star. The latest Gaia data has helped tighten the distance estimate, but the age tension remains. A third possibility, which is interesting but speculative, is that the universe itself is slightly older than we think. The 13.8 billion year age comes from very precise measurements of the cosmic microwave background, the expansion rate, and other indicators. These measurements have small uncertainties of their own. If the universe is, say, 14 billion years old instead of 13.8, the tension with the Methusela star largely disappears. But there's a problem with this idea too. There's actually a known disagreement about the age of the universe. Different methods give slightly different answers. Measurements based on the cosmic microwave background give one number. Measurements based on the local expansion rate give a slightly higher number. This is called the Hubble tension, and it's one of the biggest unsolved problems in cosmology. If the local expansion rate is right, the universe might be slightly younger than the CMB suggests, which would make the Methusela problem worse. If the CMB is right, the universe is older, which might help. But the difference is only a few 100 million years, not enough to fully resolve the issue. So as of right now, the Methusela star remains a puzzle. It might be just barely younger than the universe, with the apparent age coming from accumulated small errors in our measurements. It might actually be older, in which case our cosmology is wrong somewhere. We genuinely don't know. What's wonderful about this, in a strange way, is that we have a star you can see with binoculars from your backyard, and astronomers cannot tell you for certain whether it's older or younger than the universe itself. A nearby, well-studied object, not some galaxy at the edge of space. A star 190 light-years away, and we don't know its age within 1 billion years. If you look up at the night sky and find Libra, the Methusela star is right there. The light entering your eyes left that star 190 years ago, around the time of the American Civil War. The star itself, though, has been burning since something close to the beginning of time. Every photon coming from it carries information about the very earliest universe, about a time before the sun existed, before our galaxy fully formed, before most of what we see in the cosmos came to be. That's an old star, maybe too old, maybe older than seems possible in a 13.8 billion year old universe. And it's hanging there in the constellation Libra, just visible enough to study, refusing to give us a clear answer about how old it really is. The Methusela star is a single object, just one star out of hundreds of billions in the Milky Way. But its existence suggests that something about how we measure the age of stars, or how we understand the early universe, isn't quite right. That's a hint, a clue, a single data point that doesn't fit. And science doesn't ignore data points that don't fit. It pulls on them, tries to figure out what they mean. And someday, when we understand the Methusela star better, we'll probably understand the universe better too. For now, though, it just sits there, older than seems possible. A small light in Libra that shouldn't quite be where it is. There's something else worth saying about the Methusela star before we move on. It's not the only star in this category. It's just the most extreme. Astronomers have found other stars with similar metal-poor compositions, similar age estimates, similar uncomfortable closeness to the age of the universe itself. They're called ultra-metal-poor stars, and they exist throughout the Milky Way, mostly in the galactic halo, the diffuse spherical region surrounding the disk. These stars are essentially fossils from the early universe. They formed when conditions were very different from today, when the universe was still young, when most of the heavy elements that fill our world hadn't been made yet. Studying them is like studying ancient artifacts. Each one carries information about a moment in cosmic history that we can't reach any other way. What's strange about the entire population is that some of them seem too old. Not as extreme as the Methusela star, but old enough that they're pushing against the timeline of when stars could have formed. If our models are right, the very first generation of stars would all have been short-lived. They were too massive to last. They lived for a few million years and then exploded. The second generation, formed from the debris of the first, would have included stars of various sizes, including some smaller ones that could last for billions of years. These second-generation stars should have very low metal content. The Methusela star fits this category. So do the other ultra-metal-poor stars. But the timing matters. The first generation had to live and die before the second generation could form. That takes time, hundreds of millions of years. During that time, gas had to clump together, form stars, have those stars run their full life cycle, and then explode and scatter their material back into space. Only then could the second generation form. The Methusela star and its peers seem to have formed at the very earliest possible moment for second-generation stars, the very edge of the timeline, right at the moment when the second generation became possible, which is impressive enough on its own, even before we consider the difficulty of measuring their ages precisely. This is one of those situations where multiple lines of evidence point to the same conclusion. The early universe was different from we predict. Stars formed earlier than expected. Galaxies grew faster than expected. Black holes appeared before they should have been able to. And ancient individual stars seem to have existed almost as soon as it was physically possible for them to exist. Whatever's happening in the early universe, our models aren't capturing all of it. There's something missing. Something about the rate of star formation, or the timing of cosmic structure, or the nature of dark matter, or the physics of the Big Bang itself that doesn't match what we're seeing. The Methusela star is one of the closest individual examples of this mismatch. A star you can see with binoculars from your backyard. A star that was probably forming when the universe was barely young enough to support stars at all. A star that, by every measurement we can make, is uncomfortably old, just sitting there, glowing dimly, daring us to figure out how it can be that old. Now let me tell you about black holes that were born already massive. The early universe shouldn't have had supermassive black holes. The math doesn't work. There hasn't been enough time, and yet, when we look out into the deepest reaches of space, we find them anyway. Enormous, fully grown black holes that existed when the universe was less than 1 billion years old. Black holes containing the mass of billions of suns in a universe that's barely had time to make any suns at all. This is one of the most stubborn problems in modern cosmology, the early supermassive black hole problem. And the leading explanation might be one of the strangest objects in physics: direct collapse black holes. Giants that didn't form from stars. Giants that formed directly from collapsing clouds of gas, skipping the entire stellar phase of cosmic evolution. To explain why this is so weird, we need to talk about how black holes are supposed to form. The standard story is this: a massive star runs out of fuel. Without fusion pushing outward, gravity wins, and the star's core collapses. If the core is heavy enough, more than about 3 times the mass of our Sun, no known force can stop the collapse. The matter falls in on itself infinitely until it forms a black hole. The black hole that's left over has a mass roughly comparable to the star that made it, maybe 10 or 20 solar masses, sometimes a little more. These are called stellar mass black holes, and we know thousands of them exist in the Milky Way alone. To get a supermassive black hole, the kind found at the centers of galaxies with millions or billions of solar masses, you need to grow a stellar mass black hole. You feed it gas. You let it merge with other black holes. Over time, it gets bigger. This process can produce huge black holes given enough time, but it's slow. There's a fundamental limit on how fast a black hole can grow by eating matter. It's called the Eddington limit, and it comes from a basic physical balance. As matter falls toward a black hole, it heats up. As it heats up, it emits radiation. The radiation pushes outward on incoming matter. If the radiation gets too intense, it pushes matter away faster than the black hole can swallow it, and the black hole stops growing. The Eddington limit defines the maximum rate at which a black hole can accumulate mass while still allowing radiation pressure to escape. Black holes can't exceed the Eddington limit for very long. The math is well understood. And the math says that to grow from a stellar mass seed of about 10 solar masses up to a supermassive black hole of 1 billion solar masses, you need a long time, hundreds of millions of years at minimum, even if the black hole is feeding at the Eddington limit continuously, which they don't usually do. So when we look at the very early universe and find supermassive black holes containing billions of solar masses, we have a problem. The universe wasn't old enough to grow them. The James Webb Space Telescope has been finding more and more of these. UHZ-1, a supermassive black hole detected in 2023, was already about 10 million solar masses when the universe was only 470 million years old. That's an enormous black hole at an absurdly early time. Other Webb observations have found similar monsters. By every model we have, these black holes shouldn't have had time to grow that big, and yet there they are. So how did they form? This is where direct collapse black holes come in. The idea is simple. In the very early universe, conditions might have been right for enormous clouds of gas to collapse directly into black holes without first becoming stars. Here's how it would work. In a region where the gas was extremely pure, mostly hydrogen and helium with no heavy elements, and the radiation environment was right to prevent the gas from cooling and fragmenting into individual stars, an entire massive cloud might collapse all at once. Instead of forming many stars, it would form a single object, a direct collapse black hole. The seed mass would be enormous, somewhere between 10,000 and a million solar masses, already supermassive at birth. If this happened, then by the time the universe was a few 100 million years old, you'd have black holes that already had a huge head start. They'd grow from massive seeds rather than tiny stellar remnants. Even at normal Eddington limited growth rates, they could reach billions of solar masses by the time we see them in the early universe. The conditions required are specific. You need a cloud of gas with very low metal content. You need ultraviolet radiation from nearby galaxies to keep the gas hot enough that it doesn't fragment into stars. You need the cloud to be massive enough that gravity wins and the whole thing collapses at once. And you need this to happen within the first few 100 million years after the Big Bang. These conditions might have existed in the early universe, briefly in some regions. The exact requirements are still debated. Different research groups have proposed different scenarios for how direct collapse black holes form. But the general idea has gained significant traction over the past decade as the early supermassive black hole problem has gotten more severe. In 2024, astronomers using Webb identified what might be the strongest direct evidence yet for a direct collapse black hole. A galaxy designated GN-Z11, which existed when the universe was only 400 million years old, contains a black hole that's about a third of the entire mass of the host galaxy. That's bizarre. In the modern universe, supermassive black holes are typically about 1 part in 1,000 of their host galaxy's mass. But this one is enormous compared to its galaxy. The simplest explanation is that the black hole formed first, before most of the galaxy did, which is exactly what direct collapse predicts. Another candidate is UHZ1, which I mentioned earlier. It also seems to have a black hole that's overweight compared to its host galaxy. Multiple early universe observations point to the same picture. Black holes that were born already massive and grew alongside their host galaxies, rather than starting small and growing slowly inside them. But here's the strangeness. We don't have direct proof that any object formed by direct collapse. We have indirect evidence, the existence of these overweight early black holes, that something happened. We have theoretical models showing direct collapse is possible under certain conditions. We have hints from Webb data, but we've never actually observed a cloud of gas collapsing directly into a black hole. We've never caught one in the act. This means direct collapse black holes are somewhere between speculative and probable. They're a leading explanation, but they're not confirmed. Maybe they exist. Maybe something else explains the early supermassive black holes we keep finding. Maybe both. What's strange to think about is what these objects would have been like in the moment they formed. Imagine a region of the early universe, just a few 100 million years after the Big Bang. The first stars are starting to ignite elsewhere. The universe is getting brighter. And in this one region, an enormous cloud of pristine hydrogen and helium begins to collapse. Not into stars, not into a galaxy, into a single object. A black hole that's born with a mass of 100,000 suns or more. There's no flash of light when it forms, the way there is when a massive star collapses into a black hole. No supernova. The matter just falls inward, and at some point it crosses the event horizon, and then it's gone. A black hole exists where there used to be a cloud of gas, and it's already among the biggest black holes the universe will ever produce. That's the candidate explanation for the early supermassive black holes. Objects that skipped the stellar phase entirely. Objects that were born already massive. If they exist, and the evidence increasingly suggests they do, they're some of the strangest things in the universe. Black holes without progenitor stars, direct collapses from primordial gas, giants from a moment in cosmic history that was barely the beginning. We might find direct evidence in the next few years. Webb might catch one forming, or its immediate aftermath somewhere in the early universe. Or astronomers might rule out direct collapse and discover that early supermassive black holes formed by some even stranger process. Either way, this question is going to push the boundaries of what we know about how things in the universe come to exist. The black holes are out there. They formed somehow. Our job is to figure out how. And so far, every answer we come up with is uncomfortable. Now let me tell you about a galaxy cluster that's too heavy. About 7 billion light-years from Earth, in the constellation Phoenix, there's a galaxy cluster so massive it has its own nickname, El Gordo, Spanish for the fat one, and astronomers chose the name carefully, because El Gordo is, by some measurements, the most massive galaxy cluster ever detected at its distance, possibly too massive to fit comfortably in our standard model of cosmology. Let me set up why this matters. A galaxy cluster is a collection of hundreds or thousands of galaxies, all gravitationally bound together. They're the largest gravitationally bound structures in the universe. Within a cluster, galaxies orbit each other in slow, complicated paths, sometimes colliding and merging, all held together by their mutual gravity and by an enormous halo of dark matter that surrounds and pervades the cluster. Galaxy clusters are also some of the most useful objects in cosmology. By measuring how massive they are and how they're distributed through space, astronomers can test their models of how the universe formed and evolved. The standard model of cosmology, called lambda CDM, makes specific predictions about how many massive clusters should exist at different distances. The earlier we look in cosmic time, the smaller and rarer the most massive clusters should be, because gravity hasn't had as long to assemble them. El Gordo is at a distance of about 7 billion light-years, which means we're seeing it as it existed when the universe was about half its current age. At that point, the universe should have been actively building galaxy clusters, but the most massive ones should still have been relatively rare and not yet at their final size. Then El Gordo showed up. It was first identified in 2011 by the Atacama Cosmology Telescope in Chile, using a technique called the Sunyaev-Zeldovich effect, which detects clusters by the way they distort the cosmic microwave background. Follow-up observations with Hubble, Chandra, and other instruments confirmed it was a real cluster, and that it was massive, really massive. The early estimates put El Gordo at about 3 quadrillion times the mass of the Sun. That's 3 followed by 15 zeros. For context, our entire Milky Way galaxy contains roughly 1 trillion solar masses, including dark matter. El Gordo is 3,000 times heavier than the Milky Way, and it's 7 billion light-years away, meaning we're seeing it from a time when the universe was about half as old as it is now. A more recent analysis by James G. at Yonsei University, published in 2023, used gravitational lensing to refine the mass measurement. Gravitational lensing is the bending of light by mass, predicted by Einstein's general relativity, and it's one of the most reliable ways to measure how much matter is in a region of space, including dark matter. The new measurement put El Gordo at so 2.1 quadrillion solar masses. Still huge, still extreme. The problem is that according to the standard cosmological model, clusters this massive at this distance should be vanishingly rare. Some calculations suggest that the probability of finding a single cluster as massive as El Gordo at its observed distance in the volume of universe we can survey is something like 1 in 100, maybe lower. That doesn't mean it can't exist. Rare things happen. If you look long enough and far enough, you'll occasionally find an outlier. Statistically, El Gordo could be that outlier, the one extreme case in our observable universe. But El Gordo isn't alone. Astronomers have found other extremely massive clusters at similar distances. Their existence, taken together, has been used to argue that the standard cosmological model might be slightly off. Maybe structure formed faster in the early universe than our models predict. Maybe dark matter behaves differently from what we assume. Maybe there are corrections to gravity at large scales. Or maybe we're just looking at a string of statistical coincidences. There's another wrinkle. El Gordo isn't a single relaxed cluster. It's actually two clusters in the process of merging. Astronomers can see this in the X-ray emission from the hot gas between the galaxies. The gas has been disturbed and shock-heated by the collision. There's a clear pattern of two cores moving past each other at high speed. The merger is one of the most violent events ever observed in the universe. This raises an interesting question. Should we count the mass as one object or two? The two component clusters individually wouldn't be quite as record-breaking. It's their combination that pushes El Gordo into rule-breaking territory. But the same is true for many massive clusters, including local ones like Abell 2744, called Pandora's cluster, which is also a merger of multiple smaller clusters. These mergers happen all the time. They're part of how clusters grow, and the mass calculations include all the matter involved, so the total is a fair measurement of how much stuff has accumulated in that region of space. By that measure, El Gordo is genuinely one of the most massive things in the universe at its distance. Possibly, impossibly massive. Some researchers have argued that the existence of El Gordo, combined with other observations, points to something called the cosmological tension. The standard model predicts certain things about the rate of structure formation. If those predictions don't match observations, something needs to change. There's also another tension related to El Gordo, specifically. The way the gas inside the cluster is distributed, the way the galaxies are moving, all suggest that the merger happened with extreme velocity. Some calculations suggest the two component clusters were approaching each other at thousands of kilometers per second before the collision. That's also at the edge of what standard cosmology predicts, because such high velocities require very strong gravity from a very massive system. Other researchers have pushed back. They've argued that the original mass estimates were too high, that El Gordo is unusual but not unprecedented, that with more careful modeling, the tension goes away. Science is messy. Different teams disagree about how serious the problem really is. What's clear is that El Gordo is real. It's enormous, and it's at a distance where finding such an object pushes against the standard model. Even if it's not definitive proof of new physics, it's a hint, a clue, a piece of evidence that things at the largest scales might be slightly different from what we assume. If you could somehow stand inside El Gordo, you'd be surrounded by hundreds of galaxies, each containing billions of stars, all locked in a chaotic dance with each other. The light from billions of suns would fill the sky. The gas between the galaxies, heated to tens of millions of degrees by the merger, would be glowing in X-rays. You'd be in one of the densest concentrations of matter in the universe, watching one of the most violent events in cosmic history. But you'd also be in something the standard model says shouldn't easily exist. A monster. A statistical outlier. A pile of mass too big for its age. El Gordo is out there right now, 7 billion years in the past, doing whatever it's doing. The light we see from it left when our solar system was already in existence, but Earth was just a young planet. By the time the light reached us, El Gordo had aged 7 billion more years. The cluster, as it exists today, has probably evolved further. We might never know exactly what it's like in the present moment, because the light from then hasn't reached us yet. But what we can see, the version from 7 billion years ago, is enough to tell us something important. The universe builds bigger structures faster than our models predict, and we don't quite know why. That's enough of a clue to keep cosmologists up at night. There's another aspect of El Gordo worth considering. The cluster isn't just massive, it's hot. The gas between the galaxies, the intracluster medium, is at a temperature of roughly 200 million degrees. 200 million. That's not a typo. The gas is heated to the point where ordinary matter ceases to exist as atoms. Electrons are stripped from their nuclei. The gas becomes a plasma glowing in X-rays. This is hotter than typical clusters. The Coma cluster, a familiar nearby cluster, has gas at about 100 million degrees. Already extreme. El Gordo is twice as hot, and the temperature reflects the depth of the cluster's gravitational well. The hotter the gas, the more massive the cluster, because gas only gets that hot when it's been compressed by tremendous gravitational forces. The X-ray observations of El Gordo show distinct features that confirm the merger story. There are two hotspots in the gas, corresponding to the cores of the two component clusters. There's a tail of gas extending behind the smaller core, stripped from it by the collision. There's a region of compressed, ultra-hot gas between the cores, where the two cluster atmospheres are smashing into each other. All of these features match what computer simulations predict for major mergers. But the simulations also predict that mergers like El Gordo should be rare in the early universe. The most violent mergers should happen later in cosmic history, when clusters have had time to grow large enough to collide energetically. Finding such an extreme merger 7 billion years ago, when the universe was half its current age, suggests that cluster building has been happening faster than expected. There's also the question of what El Gordo will become. The two cores are currently moving past each other at high speeds. They'll separate, slow down, reverse, and eventually merge into a single cluster. This process takes billions of years. By the time El Gordo finishes merging, it will be one of the most massive single clusters in its part of the universe. A truly enormous gravitational system with thousands of galaxies all bound together. We can't watch this happen, of course. The light from El Gordo today shows us a moment from billions of years ago. The current state of the cluster in real cosmic time is something we'll never see. Light from now will reach us in 7 billion years, but by then we'll probably be gone. The Earth might still be here, but human civilization probably won't be. So El Gordo's full evolution is hidden from us by the simple geometry of light travel time. We can simulate what the future of the cluster looks like. Based on its current state and the laws of physics, we can extrapolate forward. The simulations show a complete merger, eventual relaxation into a stable system, and continued growth as more galaxies fall in from the surrounding intergalactic space. By the time the universe is double its current age, El Gordo will be a fully formed monster cluster, comparable to the most massive systems we know in the local universe. But that's the future. What we see is the present moment in El Gordo's history, frozen by the time it took the light to reach us. A snapshot of a violent collision captured 7 billion years ago. A snapshot of a system that, by our current cosmological theories, should be rarer than it appears. And it suggests that something about how the universe builds large structures might need refining. Either our cosmological parameters are slightly off, or our simulations don't capture all the physics involved, or there's a process we haven't fully accounted for. Whatever the explanation, El Gordo and its peer extreme clusters are pushing astronomers to think harder about what they thought they understood. The cluster is out there doing whatever it's doing in the present moment. We see only the past. And the past, as captured in El Gordo's 7-billion-year-old light, is already extraordinary. Now, let me tell you about a wall in the universe that's bigger than anything we know how to build. There's a structure in the universe so large that, according to our current understanding of cosmology, it has no business existing. Not because it violates any law of physics directly, but because there hasn't been enough time since the Big Bang for it to have formed. This structure is called the Hercules Corona Borealis Great Wall. It's roughly 10 billion light-years long, and it represents one of the most direct challenges to the standard model of cosmology ever observed. Let me explain what this structure actually is and why its size is a problem. At the largest scales, the universe has structure. Galaxies aren't scattered randomly through space. They're organized into clusters. Clusters are organized into superclusters. And superclusters are connected by enormous filaments of galaxies, with vast empty voids between them. This pattern is called the cosmic web, and it's been mapped in increasing detail over the past few decades. The cosmic web emerged from tiny variations in the density of matter in the very early universe. Quantum fluctuations from the inflationary epoch were stretched to enormous scales, and over billions of years, gravity amplified them. Slightly denser regions attracted more matter and grew. Slightly less dense regions lost matter and became voids. The result is the web we see today. This process produces a maximum scale for structure. According to the standard cosmological model, structures larger than about 1,200 million light-years can't exist as coherent objects. There hasn't been enough time since the Big Bang for gravity to organize matter on scales larger than that. This limit is called the end of greatness, the scale above which the universe should look uniform. The Hercules Corona Borealis Great Wall is, depending on how you measure it, somewhere between 6 and 10 billion light-years long. That's roughly 8 times the maximum allowed scale. It's not a tiny exception to the rule. It's a huge violation of it. The wall was first reported in 2013 by Istvan Horvath, John Hakila, and Zsolt Bagoli. They were studying gamma-ray bursts, the most energetic explosions in the universe. Gamma-ray bursts are useful for mapping the large-scale structure of the cosmos because they can be detected across vast distances, much farther than ordinary galaxies. By plotting the positions of gamma-ray bursts in 3-dimensional space, you can see the underlying distribution of matter at scales no other technique can reach. What Horvath and his colleagues found was a clustering of gamma-ray bursts in a particular region of the sky, in the direction of the constellations Hercules and Corona Borealis, at a redshift of about 1.6. That redshift corresponds to a distance of around 10 billion light-years. The clustering was statistically significant. It wasn't a random arrangement. There were actually more gamma-ray bursts in that direction than would be expected. The estimated extent of the clustering, the longest dimension across which the gamma-ray bursts seemed to be associated, was enormous. Different analyses have given different sizes, ranging from about 6 billion light-years up to 10 billion light-years. Even the most conservative estimate makes this structure dramatically larger than the maximum scale predicted by the standard cosmological model. The probability that this clustering happened by chance was estimated to be very low, less than a fraction of a percent. So either the gamma-ray bursts genuinely trace a real structure of unprecedented size, or our statistical analysis is wrong somewhere. There has been pushback. Some astronomers have argued that gamma-ray bursts are biased traces of large-scale structure. They tend to occur in star-forming galaxies, which are more common in some regions than others. Maybe the apparent clustering reflects variations in the rate of gamma-ray bursts rather than an actual physical structure. Others have argued that the statistical analysis didn't fully account for selection effects. The gamma-ray bursts in the sample were detected by various instruments with different sensitivities and different sky coverage. These observational biases could create apparent structure where none exists. But other analyses have largely confirmed the original finding. The clustering seems to be real. Whether it represents a single coherent structure or just a region of enhanced density is harder to determine. But something unusual is going on in that part of the sky. If the Hercules Corona Borealis Great Wall is a real structure, it has profound implications for cosmology. The standard cosmological model is built on a principle called the cosmological principle. This principle states that the universe is homogeneous and isotropic at large scales. It looks the same in every direction, and its average density is the same everywhere, once you average over scales larger than about 300 million light-years. The cosmological principle is one of the foundational assumptions of modern cosmology. Almost everything we know about the universe at large scales depends on it. A structure 10 billion light-years across would violate the cosmological principle. It would mean that the universe is not homogeneous at the largest scales. There would be a part of the universe with significantly more matter than other parts, on a scale where the principle says no such variation should exist. If the cosmological principle is wrong, even slightly, it would force a major revision of cosmology. Our calculations of the universe's age, the rate of expansion, the amount of dark matter and dark energy, would all need to be reconsidered. The implications cascade. Most cosmologists are reluctant to abandon the cosmological principle based on a single anomalous structure, especially one detected through gamma-ray bursts, which are relatively rare and hard to use for precision measurements. They prefer explanations that preserve the standard model. One possibility is that the Hercules Corona Borealis Great Wall isn't a single coherent structure. Maybe it's an alignment of several smaller structures that just happens to look like one big thing from our viewing angle. This kind of projection effect is real. We've fooled ourselves before by mistaking aligned objects for connected ones. Another possibility is that gamma-ray bursts are tracing some local enhancement that doesn't reflect the underlying matter distribution. Maybe the gamma-ray bursts cluster together because of some physical process related to their progenitors, not because the matter they sit in is unusually clumped. A third possibility is that we're seeing a real structure, but it's smaller than originally claimed. Maybe it's 3 or 4 billion light-years long instead of 10. Still bigger than the end of greatness, but less of an extreme outlier. And a fourth possibility is that the cosmological principle is wrong and the wall is real, and we have a serious problem with our model of the universe. Astronomers continue to study the region. More gamma-ray bursts are detected every year. More distant galaxies are being mapped with surveys like the Sloan Digital Skies Survey and DESI. Eventually, with enough data, we'll know whether the wall is real or an illusion. But here's the thing. Even if the Hercules Corona Borealis Great Wall turns out to be smaller than initially claimed, or to be a projection effect rather than a real structure, the issue doesn't go away. There are other large structures in the universe that also push against the end of greatness. The Sloan Great Wall, the South Pole Wall, the Giant Arc, the Big Ring. Each of them pushes the limit. None of them quite as extreme as Hercules Corona Borealis, but together they suggest that something might be off about our understanding of how matter is distributed at the largest scales. If you could somehow stand outside the universe and look at the cosmic web, The Hercules Corona Borealis Great Wall, if it exists, would be one of the most striking features. Imagine a thread of matter running across roughly 1/10 of the entire observable universe. A coherent structure on a scale that defies our models. A pattern in the cosmic foam that shouldn't have had time to form. It's out there now, somewhere in the direction of Hercules and Corona Borealis, at a distance of about 10 billion light-years. Whatever's actually there is a structure or alignment of objects that emerged from the early universe and survived to leave its imprint on the gamma-ray burst distribution we see today. We'll keep looking, we'll keep measuring, and someday we'll know whether the wall is real or an illusion or something in between. Until then, it remains one of the strangest features of the cosmos. A structure that pushes against the limits of how big anything in the universe is allowed to be, and might exist anyway. And it isn't the only one. Let me tell you about a ring of galaxies that defies our cosmological models. In 2024, a graduate student named Alexia Lopez at the University of Central Lancashire announced the discovery of another structure that violates the cosmological principle. She called it the Big Ring, and it sits in roughly the same region of the sky as another structure she'd already found, called the Giant Arc. Both of these structures push against the same problem as the Hercules Corona Borealis Great Wall. They're too big to fit comfortably in the standard model, and the fact that two of them sit near each other at similar distances makes the problem worse. Let me describe what Lopez found. In 2021, Lopez and her colleagues announced the Giant Arc. They were analyzing the spectra of distant quasars, which are extremely bright objects powered by supermassive black holes in the early universe. By looking at the absorption lines in quasar spectra, you can detect the gas and dust between us and the quasar, including any galaxies along the line of sight. By plotting the positions of these absorbing galaxies in 3 dimensions, you can map the distribution of matter at distances no other technique can reach. What Lopez found was an enormous arc of galaxies curving across roughly 3.3 billion light-years at a distance of about 9.2 billion light-years from Earth. The arc was visible in absorption lines from many different quasars, suggesting that the structure was coherent and large rather than a few coincidentally aligned galaxies. That's already a problem. 3.3 billion light-years is far larger than the end-of-greatness scale of about 1,200 million light-years. The giant arc is too large to fit inside the standard cosmological model. Lopez calculated the probability that the arc was a chance alignment of unrelated galaxies. The result was about 1 in 17,000. That's pretty significant. Not airtight, but suggestive of a real structure. Then in 2024, Lopez found another one. The Big Ring is roughly 1.3 billion light-years in diameter, slightly larger than the end of greatness. And it's at the same distance as the Giant Arc, in roughly the same part of the sky. Same redshift of about 0.8, corresponding to about 9.2 billion light-years. So, we have 2 enormous structures, both bigger than they should be, both at the same distance, both in the same region. That's suspicious. 2 improbable structures right next to each other, by chance, would be remarkable. Either there's something special about that region of space, or the standard model has a problem. Lopez calculated the statistics. The probability of finding the Big Ring on its own was about 1 in 200. The probability of finding both the Giant Arc and the Big Ring near each other was even lower. Together, they represent a significant challenge to the assumption that the universe is uniform at the largest scales. These structures, like the Hercules Corona Borealis Great Wall, push against the cosmological principle. They suggest that the universe might be lumpier at the largest scales than our standard model allows. Something is happening in a region 9 billion light-years away that shouldn't be possible according to our equations. There are several proposed explanations. One possibility is that the structures are real, and our cosmological model needs to be modified. Maybe gravity behaves differently at very large scales. Maybe there are corrections to general relativity that become important at distances we haven't been able to measure precisely. Maybe dark energy, the mysterious force driving the accelerating expansion of the universe, isn't quite what we think it is. Another possibility involves something called cosmic strings. These are hypothetical one-dimensional defects in space-time, predicted by some theories of physics but never directly observed. If cosmic strings exist, they could create enormous structures in the universe by gravitationally attracting matter along their length. The giant arc and the big ring could be the imprint of cosmic strings on the distribution of galaxies. This would be incredible, because it would be the first direct evidence that cosmic strings actually exist. A third possibility is that the structures are statistical flukes. The probabilities I quoted are low, but they're not zero. If you survey a large enough volume of space, looking for structures of a particular type, you'll occasionally find something rare. The Lopez team has been careful with their statistics, but it's possible they're seeing patterns that aren't really there. A fourth possibility involves a phenomenon called baryon acoustic oscillations. These are wrinkles in the distribution of matter that came from sound waves traveling through the early universe. They have a characteristic scale of about 500 million light-years, much smaller than the Big Ring. But maybe there's some related phenomenon we haven't fully understood that produces larger features. A fifth possibility is even more speculative. Some theories of inflation, the brief period of exponential expansion in the early universe, predict that we might see fossil imprints of pre-inflationary physics in the current universe. If the universe before inflation had structure on certain scales, that structure could have been stretched to enormous sizes during inflation, and we'd see it today as anomalously large features. The Big Ring and giant arc could be exactly that kind of fossil. Right now, all of these possibilities are on the table. The structures are still being studied. More observations are needed. Lopez and her team continue to analyze quasar absorption data, looking for confirmation that the arc and ring are real, and looking for other structures of similar size that might either support or undermine their findings. What's interesting is that both the giant arc and the Big Ring are reminiscent of features we can describe with simple geometry. An arc, a ring, curves. The cosmological principle says structures at very large scales should look like random distributions of matter, statistically uniform with no preferred direction or shape. But these features have shape. They're geometric. They look organized. That's hard to explain with random fluctuations. Random patterns rarely produce arcs or rings spanning billions of light-years. Something organized them. Whether that something is a cosmic string, or a fossil of pre-inflationary physics, or some new kind of process we haven't imagined, is exactly what astronomers are trying to figure out. Imagine flying out to a distance of 9 billion light-years. You'd be looking back 9 billion years in cosmic time to a moment when the universe was much younger. And there, all around you, would be galaxies, but they wouldn't be distributed evenly. Some of them would be arranged in the shape of a vast curving arc, 3 billion light-years long. Nearby, others would be arranged in a ring more than 1 billion light-years across, both structures pulling matter in patterns that defy easy explanation. That's the universe Lopez and her colleagues are mapping. Not a smooth, uniform cosmos, but one with hidden geometry, with shapes that hint at something we haven't understood yet. And the closer we look, the more shapes seem to appear. Now let me tell you about something pulling on us right now that we cannot see. Right now, as you sit listening to this, You and the entire Milky Way galaxy are being pulled towards something we can't see. Not gravitationally bound to it, just falling toward it. A massive concentration of mass, somewhere in the direction of the constellation Centaurus, hidden behind the disk of our own galaxy, exerting gravitational influence over thousands of galaxies, including ours. It's called the Great Attractor, and it's one of the strangest features of our cosmic neighborhood. We can't see it directly. We don't fully understand what it is, but its gravitational pull is undeniable, and the implications are unsettling. Let me explain how we discovered it. Galaxies don't sit still in space. They move. They have velocities relative to each other, driven by gravity and the overall expansion of the universe. By measuring how galaxies move, you can map the distribution of mass that's pulling on them. In the 1970s and 80s, astronomers noticed something strange. The Milky Way and its neighboring galaxies, including Andromeda, weren't moving in the way they should be if the universe were perfectly uniform. There was a coherent flow. The Milky Way, and many of the galaxies around us, were all moving in roughly the same direction, toward something massive enough to be pulling on us at a speed of about 600 kilometers per second. This flow was named the cosmic flow, or sometimes the streaming motion. And the source of the gravitational pull, wherever it was, became known as the Great Attractor. Here's the problem. The direction of the flow points toward a region of the sky that's almost directly behind the disk of the Milky Way. From our position inside the galaxy, the gas and dust in the Milky Way's disk blocks our view of whatever is on the other side. This region is called the zone of avoidance, because it's the part of the sky where we can't see distant objects clearly. So the Great Attractor was hiding. We could feel its gravity. We could measure the flow of galaxies toward it. But we couldn't actually see what it was, because our own galaxy was in the way. Astronomers had to use creative techniques to peek behind the Milky Way. They used radio observations, which can penetrate the dust better than visible light. They used X-ray observations, which can detect the hot gas in galaxy clusters. They used infrared observations, which see through dust more effectively than optical light. Slowly, over decades, they pieced together a picture of what's behind the zone of avoidance. What they found was the Norma cluster, a large galaxy cluster about 250 million light-years away. It's massive, about 1,000 trillion solar masses. That's substantial, but it wasn't massive enough to fully account for the cosmic flow. Something else was contributing. In the late 1990s and early 2000s, astronomers began to realize that the Great Attractor was larger and more complex than initially thought. It wasn't just one cluster. It was a region of enhanced density extending over a significant volume of space, with the Norma cluster as one prominent component. And then, beyond the Great Attractor, even further away, there was something even bigger, the Shapley supercluster. About 650 million light-years from us, containing roughly 20,000 galaxies and a total mass of about 10,000 trillion solar masses. 10 times more massive than the Great Attractor itself. It turned out that the Great Attractor was just the closest part of a much larger gravitational system. The Milky Way is being pulled toward the Great Attractor, but the Great Attractor itself is being pulled toward the Shapley supercluster, and both are part of a larger network of gravitational interactions that we're only beginning to map. In 2014, a team led by Brent Tully at the University of Hawaii published a paper that reframed the entire structure of our cosmic neighborhood. They mapped the flow of galaxies in 3 dimensions, and they identified a coherent structure that includes the Milky Way, the Great Attractor, and the Shapley supercluster, along with other galaxy groups and clusters. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is enormous, about 520 million light-years across. It contains about 100,000 galaxies, and the Great Attractor is essentially the gravitational valley at its center. All the galaxies in Laniakea are slowly falling toward this central point, including the Milky Way. So that's the picture today. The Great Attractor is the central gravitational basin of Laniakea, our home supercluster. It's not a single object. It's a region of enhanced density, with the Norma cluster as the most prominent component, surrounded by other massive structures, all hidden behind the disk of our galaxy. But here's what's still strange. Even though we now understand that the Great Attractor is part of a larger structure, we still can't see it clearly. The zone of avoidance still blocks our view. We're inferring its existence and structure from gravitational effects and from peeking through the dust at certain wavelengths. We've never actually had a clean optical image of the heart of the Great Attractor. There's something unsettling about that. We know there's an enormous concentration of mass pulling on us. We know it's pulling thousands of galaxies, including ours, toward it at hundreds of kilometers per second. But it's hiding. The geometry of our own galaxy puts the Great Attractor exactly behind the disk, in the worst possible location for direct observation. What's even more disorienting is the scale of the motion involved. We're moving at 600 kilometers per second toward the Great Attractor. But this motion isn't going to result in us actually arriving there in the foreseeable cosmic future. Even at that speed, it would take us hundreds of millions of years to reach the Norma cluster. And the universe is expanding, which complicates things further. In the very long run, the expansion of the universe will probably win, and the Milky Way will never actually reach the Great Attractor. But in the meantime, we're falling in slow motion towards something we can barely see. There's another mystery here. The Great Attractor and the Shapley supercluster, taken together, seem to be only part of the explanation for the cosmic flow. Some studies suggest that there's an additional component pulling matter even further than Shapley, something called the dark flow, though that name has become controversial because the original analysis has been challenged by later work. The idea of dark flow was that on top of the gravitational pull from the Great Attractor and Shapley, there's an additional bulk motion of galaxies in our region of the universe, suggesting a much larger and more distant structure pulling everything together. If the dark flow is real, it would mean there's something outside the observable universe exerting gravitational influence on matter inside it. That would be remarkable. The original studies that claimed to detect dark flow have been disputed. More recent analyses suggest it might not be real, or at least not as significant as initially thought. But the question isn't fully settled. There might be additional gravitational structures beyond what we've mapped, and they might be contributing to the motion of galaxies in ways we don't fully understand. What's beautiful and humbling about all this is the realization that our place in the universe isn't quiet. We're not just sitting in space, we're falling. The whole local supercluster is in motion, drawn by the gravity of distant masses. We're part of a vast cosmic dance, with Laniakea slowly compressing toward its center, while at the same time being pulled apart by the expansion of the universe. The Milky Way's motion isn't simple. We're orbiting the center of our galaxy. Our galaxy is moving toward Andromeda, which is gravitationally bound to us. The local group is moving as a whole toward the Virgo cluster. The local group, the Virgo cluster, and many other groups are all falling toward the Great Attractor. And the Great Attractor is being pulled toward the Shapley supercluster. Each motion is layered on top of the others, We're falling within, falling all the way out to the edge of the observable universe. The gravitational architecture of the cosmos is fractal, with structure at every scale, and we're embedded inside it. The Great Attractor is the closest visible expression of this. The thing we can almost see, but not quite. The mass that's pulling on us right now, hiding behind our own galaxy, drawing us in slow motion across hundreds of millions of years towards something we still don't fully understand. Look up at the constellation Centaurus on a clear night, if you're in the southern hemisphere, and behind those visible stars, hidden in the dust of the Milky Way's disk, is the Great Attractor. Its gravity reaches across hundreds of millions of light years to where you're standing. It pulls on the planet beneath your feet. It pulls on you right now, while you listen to this. We're all moving toward it, and we don't know exactly what's there. Now we're getting to the final three, the big ones, the ones that should not exist by any standard. Stars and black holes that push the absolute limits of what physics allows. Let me tell you about the largest star ever measured. Stevenson 2-18 is the largest star astronomers have ever measured. Not the most massive, that title belongs to other stars, but the largest by physical size. Its radius is about 2,150 times that of our Sun. 2,150. To put that number in human terms, if you replaced our Sun with Stevenson 2-18, the surface of the star would extend out past the orbit of Saturn. Earth would be deep inside it. Mars would be deep inside it. Jupiter would be deep inside it. The entire inner solar system would be swallowed. Saturn might just barely be at the surface, depending on which estimate you use. Light, traveling at 300,000 kilometers per second, would take about 8 hours to cross the diameter of this star. That's not a star. That's a region of space, the size of part of a solar system that happens to be glowing. And here's the thing. Stars this large push the limits of what stars can be. The physics says they should fall apart. But Stevenson 2-18 is out there, about 19,500 light-years away, in the constellation Scutum, sitting inside a young star cluster called Stevenson 2, and astronomers are trying to figure out how it's holding itself together. Let me explain why this is a problem. A star is a balance between two forces. Gravity pulls the matter inward, trying to collapse the star into a point. Outward pressure, generated by nuclear fusion in the core, pushes back against gravity. When these forces balance, you have a stable star. When they don't, the star either collapses or blows itself apart. In small stars like the Sun, this balance is straightforward. Hydrogen fuses into helium in the core. The energy released creates pressure. Pressure pushes outward against gravity. The star stays roughly the same size for billions of years. In bigger stars, the balance gets more delicate. As stars get more massive, the radiation pressure they generate grows faster than gravity does. There's a theoretical limit, called the Eddington limit, beyond which the radiation pressure should overwhelm gravity entirely. The outer layers of the star would be blown away by the intensity of the radiation coming from the core. The star couldn't hold itself together. For the most massive stars in the universe, this limit corresponds to roughly 200 to 300 solar masses. We don't really see stars more massive than that, though there are a few candidates that come close. The Eddington limit seems to set a hard upper bound on stellar mass. But Stevenson 2-18 isn't necessarily violating the Eddington limit. The estimates of its mass are uncertain. It might be somewhere between 30 and 100 solar masses. That's massive, but not record-breaking. The strangeness of Stevenson 2-18 isn't its mass, it's its size. How did a star with a relatively normal mass end up so enormous? The answer is that Stevenson 2-18 is a red supergiant, the final stage of life for a massive star. As massive stars age, their cores contract and heat up, while their outer layers expand and cool. The star puffs up to enormous proportions, becoming a red supergiant. Stars in this phase are typically 1,000 or more times the size of the Sun. But Stevenson 2-18 is at the extreme end of this process. It's puffed up to twice the size of typical red supergiants. And here's the problem. At its current size, the gravity at its surface is incredibly weak. The outer layers of the star are barely held in place. Strong stellar winds, which all stars produce to some extent, become much more effective at stripping mass from the star when gravity is weak. Calculations suggest that Stevenson 2-18 should be losing mass extremely rapidly. So rapidly that within a few thousand years, it should shed enough material to dramatically change its appearance. The fact that we see it in this state right now means we're catching it during a brief, dramatic phase of its life. A phase that might last only a few thousand years before the star transitions to something else. But there's more. The outer layers of Stevenson 2-18 aren't really in stable equilibrium. The density of the star's surface is so low, comparable to the density of laboratory vacuum, that the concept of a clear surface doesn't quite apply. The star fades from the dense core out to a diffuse atmosphere with no sharp boundary. Some calculations suggest that the outer layers are essentially convective, churning chaotically rather than sitting in stable layers. This makes the star's physics difficult. We don't fully understand how stars this enormous behave. The standard models of stellar evolution work well for stars more like the Sun, but they break down at the extremes. Red supergiants on the upper end of the size scale, like Stevenson 2-18, push our models past their reliable range. We're not entirely sure what's happening inside them. There are also debates about the size estimate. Different methods give different numbers. Some recent analyses suggest Stevenson 2-18 might be smaller than initially claimed, maybe 1,000 solar radii instead of 2,150. Still enormous. Still one of the largest stars known, but not quite as record-breaking as the original estimate. Other analyses argue for an even larger size, possibly approaching 3,000 solar radii. The uncertainty is large because the star is far away, embedded in a cluster, surrounded by gas and dust, and the techniques for measuring stellar sizes at that distance have significant systematic errors. Whatever the exact number, Stevenson 2-18 is at or near the theoretical maximum for stable stars. It's pushing the limits of what's possible in stellar physics. And it's going to die spectacularly. When a red supergiant like Stevenson 2-18 finally exhausts its fuel and its core collapses, the result is a supernova, a massive explosion that briefly outshines entire galaxies. Stevenson 2-18, when it goes, will produce one of the most powerful supernova explosions of any star in our galactic neighborhood. We might even see it from Earth, but that's likely a few 100,000 years away. In the meantime, Stevenson 2-18 sits in the constellation Scutum, glowing dimly with a distinctive red color, quietly losing mass at an incredible rate, waiting to die. It's a star that exists at the very edge of what stars can be. Any larger, and it would tear itself apart. Any unstable, in any other direction, and the same thing would happen. It exists in a precarious equilibrium that won't last long on cosmic timescales. What's strange to imagine is what it would be like to be near such a star. If our Sun were Stevenson 2-18, the daytime sky would be filled with glowing red. The star, would not be a small disk in the sky, the way the sun is. It would be the sky itself, or most of it. A vast red region taking up most of what you could see in any direction overhead. The light would be cooler than sunlight, redder, dimmer per unit area, but spread over so much of the sky that the total light would still be intense. You couldn't be on Earth. Earth would be inside the star, inside the photosphere, inside the convective layers, burned and vaporized long ago. But you could be on a planet very far out, past Saturn, past Uranus, out where the orbits are slow and the sun is just one of many objects in a darker sky. And from there, looking back inward, you'd see this enormous red glow filling a significant fraction of the sky. The largest object in your local universe, slowly puffing itself out of existence. In Scutum, 19,500 light-years away, Stevenson 2-18 is glowing red in the night sky. Astronomers are watching it through telescopes, trying to understand how a star can be that big, how matter can spread itself that thin and still be called a single coherent object. We're going to keep studying it until it explodes, or until we figure out exactly what it is, or until we realize that some of our assumptions about stellar physics need revision. Maybe all three. For now, it's the largest star we know, and it's almost too large to exist. Now, let me tell you about a black hole that eats faster than physics says it should. Phoenix A is one of the most extreme objects in the known universe. A supermassive black hole sitting at the center of the Phoenix cluster, about 5.8 billion light-years from Earth. Its mass is estimated somewhere between 5 and 10 billion times the mass of our Sun, putting it among the most massive black holes ever measured. Some theoretical models, based on extreme accretion physics, suggest it could be even larger, potentially up to 100 billion solar masses, but those upper-end estimates are speculative. The well-measured value puts it firmly in the multi-billion solar mass range. That's already extreme. Phoenix A is one of the most massive black holes ever detected. The supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A, has a mass of about 4 million solar masses. Phoenix A is roughly 1,000 times more massive than that. But its mass isn't even the strangest thing about it. The strangest thing is how fast it's growing. Let me set up the problem. Black holes grow by eating matter that falls into them. Gas, dust, stars, smaller black holes, anything that gets close enough. As matter falls in, it heats up and emits radiation. The radiation pushes outward, opposing the inward pull of gravity. If the black hole is eating fast enough, the radiation becomes intense enough to blow incoming matter away. This is the Eddington limit. A black hole can't grow faster than the Eddington limit allows, because the radiation it produces stops it from accumulating mass beyond a certain rate. For most black holes, this works as a hard upper bound on growth. They eat at or below the Eddington limit, and over billions of years, they slowly accumulate mass. Phoenix A is eating faster than this limit allows. The Phoenix cluster, the galaxy cluster that contains Phoenix A, is one of the most extreme star-forming environments in the universe. The central galaxy of the cluster is producing stars at a rate of about 740 solar masses per year. For comparison, the Milky Way produces about 1 or 2 solar masses of new stars per year. Phoenix is forming stars about 700 times faster than us. The reason is that there's a huge supply of cooling gas in the center of the cluster falling onto the central galaxy and onto the supermassive black hole. The gas is cooling so efficiently and so abundantly that it's overwhelming the usual processes that limit black hole growth. Phoenix A is eating about 60 solar masses of material per year. 60 solar masses every year. That's roughly the mass of an entire stellar cluster fed into a single black hole every 12 months. And this has apparently been going on for some time, long enough to grow the black hole to its current enormous size. By any standard calculation, this rate of growth shouldn't be sustainable. The radiation pressure should be pushing the gas away. The black hole should be self-limiting, but it isn't. There are a few proposed explanations. One possibility is that the geometry of the inflow is unusual. Most calculations of the Eddington limit assume that gas is falling onto the black hole from all directions. If the gas is falling in from a specific direction, like along a thin disk, the radiation can escape perpendicular to the inflow without pushing the inflow back. This would allow super Eddington growth in certain configurations. There's some evidence that this happens in some black holes. Another possibility is that the gas is falling in too fast for radiation to push it back. If the inflow is supersonic, the gas crashes into the black hole faster than light pressure can deflect it. This kind of rapid free-fall accretion has been proposed but is hard to sustain. A third possibility is that we're misjudging the growth rate. Maybe Phoenix A isn't really growing at 60 solar masses per year continuously. Maybe it has bursts of activity separated by quieter periods. Over long time scales, the average growth rate could be more in line with the Eddington limit. The current observation could be catching it during an unusually active phase. Whatever the explanation, Phoenix A is doing something that pushes the limits of how fast black holes can grow. And it's probably not alone. Other massive black holes in cluster centers might be doing similar things. The conditions in the most extreme galaxy clusters allow for accretion physics that doesn't apply to ordinary black holes. There's another mystery here. Where is all the gas coming from? Phoenix A is eating 60 solar masses per year. Over billions of years, that's an enormous amount of mass. Where does it come from? The answer is that the entire cluster is feeding the central region. Gas from across the cluster, including gas being shed by the cluster's many galaxies, is cooling and flowing toward the center. The center of the cluster is at the bottom of the cluster's gravitational well. Anything that loses energy ends up there. Normally, this process is balanced by feedback. The supermassive black hole, when it eats, produces jets of radiation and matter that push back against the inflowing gas, heating it up and preventing further cooling. This is called AGN feedback, and it's how black holes are thought to regulate the growth of their host galaxies. But in the Phoenix cluster, this feedback isn't working effectively. The gas is cooling faster than the black hole can heat it. The result is an enormous flow of cold gas toward the center, fueling rapid star formation in the central galaxy and rapid growth of the central black hole. It's not entirely clear why feedback fails in this cluster, but works in most others. The Phoenix cluster is unusual in several ways. It's relatively young as clusters go. Its central galaxy is the brightest cluster galaxy we know of. Its X-ray luminosity is extreme. Whatever combination of factors is involved, it's producing a system where a supermassive black hole can grow at near-record rates. What's wonderful, in a strange way, is the scale of the energetics involved. The black hole is releasing enormous amounts of energy as it eats, but it's not enough to stop the inflow. The energy released is comparable to the entire luminosity of a galaxy. Phoenix A is one of the brightest objects in the universe at certain wavelengths, simply because of how much it's eating. If you could be near Phoenix A, you'd be in one of the most violent environments imaginable. Gas falling in at significant fractions of the speed of light. Radiation intense enough to cook anything organic. Magnetic fields tearing through space at enormous strengths. Jets of matter shooting out at relativistic speeds. The accretion disk would be a hellish cauldron, glowing brighter than entire galaxies, surrounded by even brighter regions of infalling matter. And at the center, hidden behind the bright accretion flow, the black hole itself. Multiple billions of solar masses of mass crammed into a region of space less than the size of our solar system. Space-time warped to the point of disconnection. A point of no return, eating faster than seems possible. Phoenix A is doing all of this right now, 5.8 billion light-years away. The light from it is still on its way to us, traveling for billions of years across the expanding universe. By the time we see Phoenix A in our telescopes, it's already been consuming for much longer than we can measure. The black hole we observe is from a moment billions of years in the past, and the present-day version is even bigger, even more massive, even more extreme. And it's just one of many. There are other black holes in other cluster centers doing similar things. There are other extreme accretion phenomena throughout the universe. Phoenix A might be the current record holder, but it's not unique. Just the most dramatic example of an entire class of objects that push the boundaries of what black holes are supposed to be able to do. The Eddington limit was thought to be a hard limit. Phoenix A suggests it's more like a guideline. And in the most extreme corners of the universe, even guidelines bend. And now we come to the final object. The biggest, the heaviest, the most extreme. Let me tell you about TON 618. About 10.4 billion light-years from Earth, in the constellation Canes Venatici, there is a quasar. Quasars are extremely bright objects powered by supermassive black holes, feeding rapidly on infalling matter. The matter heats up so much as it falls toward the black hole that it outshines the entire host galaxy. From great distances, we can see quasars, but we can't easily see the galaxies they live in. The black hole's accretion is so bright, it drowns out everything else. TON 618 was first catalogued in 1957. For decades, it was just one of many faint blue points of light in catalogues of unusual objects. It wasn't until later, in the 1970s and beyond, that astronomers realized many of these blue points were actually quasars at enormous distances. By the time TON 618's redshift was measured, it became clear that this object was extraordinarily bright and extraordinarily distant. The light we see from TON 618 left it about 10.4 billion years ago. The universe was less than a third of its current age. Already, this quasar was doing what it was doing, blazing across the early universe with enough brightness that we can detect it from billions of light-years away. In 2004, astronomers measured the mass of the black hole at the center of TON 618 using the technique of reverberation mapping. By observing how the light from the quasar varies over time, and how those variations propagate through the surrounding gas, you can calculate the mass of the central black hole. The result was staggering. About 66 billion solar masses, 66 billion times the mass of our Sun. That makes TON 618 one of the most massive black holes ever measured, possibly the most massive by any standard. It's at the very upper limit of what black holes can be. To get a sense of the scale, imagine the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A. It has a mass of about 4 million solar masses. Sagittarius A is already enormous, far beyond anything we encounter on human scales. TON 618 is 16,500 times more massive. Or compared to the M87 black hole, the one we famously photographed in 2019. That one is about 6.5 billion solar masses. TON 618 is about 10 times more massive than that. The event horizon of TON 618 has a radius of about 1300 AU. AU is the astronomical unit, the distance from Earth to the Sun. The event horizon of TON 618 is about 1300 times wider than that distance. If you put TON 618 where our Sun is, the event horizon would extend 40 times farther out than the orbit of Pluto. It would be larger than our entire solar system, a region of space larger than our entire planetary neighborhood, from which nothing escapes. Light takes about 10 days to cross the diameter of TON 618. How does an object get this big? That's the question that makes TON 618 such a stubborn puzzle. The standard model of black hole growth involves accretion at the Eddington limit, with mergers contributing additional mass over time. Even at maximum accretion rates, growing a black hole from a stellar mass seed of about 10 solar masses up to 66 billion solar masses takes time, a long time. Calculations suggest that even with continuous Eddington limited growth, you need somewhere between 2 and 3 billion years to produce a TON 618 sized black hole. But TON 618 already had this mass when the universe was only about 3.4 billion years old. The light we see from it left 10.4 billion years ago. So at most, the black hole had a few billion years to grow. And during that time, it had to start as a seed and grow to 66 billion solar masses. That's right at the edge of what's possible. Some calculations work, others don't. It depends heavily on assumptions about the initial seed mass, the duty cycle of accretion, the role of mergers, and several other factors. The leading explanation, which we discussed earlier, is direct collapse black holes. If the seed of TON 618 was a direct collapse black hole, with an initial mass of perhaps 100,000 or 1,000,000 solar masses, then the growth time becomes much more reasonable. From 100,000 solar masses to 66 billion is still a lot of growth, but it's plausible in a few billion years of Eddington limited accretion plus mergers. Another possibility involves super Eddington growth phases. If TON 618 underwent periods of accretion above the Eddington limit, like Phoenix A might be doing today, it could grow faster than standard models predict. Geometry, viewing angles, and inflow configurations could make this possible in certain situations. A third possibility involves multiple mergers. If many smaller supermassive black holes merged together over the early history of the universe, the result could be an object as massive as TON 618. Black hole mergers do happen, and they're being detected by gravitational wave observatories. Maybe the early universe was filled with mergers that built up monster black holes. Whatever the exact mechanism, TON 618 exists. It was already enormous when the universe was young. And its existence suggests that whatever processes build supermassive black holes can work very efficiently under the right conditions. What's wonderful, almost terrifying, about TON 618 is the scale. Imagine a region of space larger than our solar system, surrounded by a glowing accretion disk that outshines an entire galaxy. The disk is shedding light at a rate that would make TON 618 visible across most of the observable universe. From our position 10 billion light-years away, we still see it as one of the brightest things in the sky at certain wavelengths, despite the enormous distance and the dimming effects of cosmic expansion. If you could somehow get close to TON 618, you'd be in one of the most extreme environments imaginable. The accretion disk would be a hellscape of superheated plasma, glowing at temperatures of millions of degrees, generating enough radiation to vaporize anything organic instantly. Magnetic fields would tear through space at strengths beyond any laboratory experiment. Jets of relativistic matter would be shooting out from near the event horizon, traveling at significant fractions of the speed of light, extending hundreds of thousands of light years into intergalactic space. And at the center, the event horizon, a boundary larger than our solar system, a surface from which no light escapes, a region where space-time is so warped that the concept of outstops applying. Whatever falls past it never returns. Whatever is inside, we can never know. Ton 618 has been doing this for 10 billion years and counting. The version we see is from 10.4 billion years in the past. The present-day version in real cosmic time is even older, possibly larger, possibly quieter, as the surrounding gas is being consumed. We'll never know exactly what it's like now. The light from now hasn't reached us yet, and never will, because it's so far away that the expansion of the universe is carrying it away faster than its light can reach us. That's TON 618, the most massive black hole we've measured, an object so large it strains our models of how black holes form. A reminder that the universe contains things that push the absolute limits of physical possibility. It's at the very top of the list of impossible objects. The biggest, the heaviest, the most extreme. And out there in Cain's Venatici, it's still going, still real, still growing perhaps, still defying our easy understanding. We've descended through 10 of the strangest objects in the known universe. From early galaxies that grew too fast, to a star that might be older than time, to black holes that were born already massive, to clusters too heavy for their age, to walls and rings and arcs at scales that defy our models, to invisible attractors and stars at the edge of stability, to black holes that bend the rules of growth. What ties them together isn't just their strangeness, it's what they're telling us. Each one of these objects is a place where our understanding of the universe runs out, where our models stop matching reality, where physics, in the form we currently know it, doesn't have a comfortable answer. That's not a failure of physics, it's the universe revealing itself. Every one of these objects is a clue, a puzzle piece, a hint that something in our picture of the cosmos is incomplete. And the work of figuring out what's missing is the work of cosmology and astrophysics in our era. Maybe in 50 years these objects will be fully explained. Maybe new telescopes will reveal that the early galaxies aren't as massive as they appear. Maybe better measurements will resolve the Methusela star's age. Maybe direct collapse black holes will be confirmed by direct observation. Maybe we'll find that the cosmological principle holds, and the great walls and arcs and rings are just statistical flukes. Maybe the Great Attractor will reveal itself, and we'll understand exactly how it formed and what it's pulling on. Or maybe not. Maybe these objects will continue to defy explanation for centuries. Maybe new ones will be found that are even stranger, even more rule-breaking. Maybe our current model of the universe is fundamentally incomplete, and figuring out what's wrong will take generations of work. Either way, these objects are out there. They exist. They were there before you started watching this. They'll be there after you turn off the screen and go to sleep. They're doing whatever strange things they do, whether or not anyone is watching, whether or not anyone understands. The universe doesn't care about our models. It does what it does. And sometimes, what it does is genuinely beyond our current understanding. Imagine for a moment what it would be like to actually visit these objects. To stand inside a galaxy that grew too fast, watching stars form in conditions that defy our equations. To orbit the Methusela star, watching its ancient light glow against the backdrop of more recent space. To approach a direct collapse black hole, peering at the boundary of an object that formed without ever being a star. To stand in the middle of El Gordo, surrounded by hundreds of galaxies, all locked in chaotic motion. To traverse the Hercules Corona Borealis Great Wall, riding along its enormous length. To trace the arc of the giant arc and the curve of the Big Ring. To feel the gravitational pull of the Great Attractor, falling towards something hidden behind the dust of our own galaxy. To watch Stevenson 2-18 puff itself out of existence, shedding mass at incredible rates. To witness Phoenix A swallow the equivalent of 60 suns every year. To finally see Ton 618 up close, an object larger than our solar system, blazing with enough energy to be visible across the universe. You'll never do any of these things, of course. None of us will. The distances are too great, the energies too extreme, the time scales too long. Even if we could travel at the speed of light, we'd be unable to reach most of these objects in any reasonable amount of time. Most of them existed billions of years ago, and the present-day versions might be very different. We're studying them from far away, through telescopes, with mathematics. That's the only way we can know them, but we do know them. That's what's remarkable. From a small planet, orbiting an ordinary star in an ordinary galaxy, on a thin shell of life clinging to a rocky surface, we have figured out that these objects exist. We've measured their masses. We've mapped their distributions. We've analyzed their light, their gravity, their motion. We've built models of how they should work and noticed when reality doesn't fit those models. That's an incredible achievement, even when it leaves us with mysteries. Maybe especially when it leaves us with mysteries, because the mysteries are how we know we're really looking at the universe, not just at our own ideas about it. If everything fit perfectly into our models, we'd suspect we were just seeing what we expected to see. The fact that the universe surprises us, that it produces objects we don't understand, that it pushes against our equations, is evidence that we're really learning about reality. These mysteries keep us honest. They remind us that no matter how clever we think we are, the universe is cleverer. That no matter how much we've figured out, there's always more. That the cosmos is bigger and stranger and more wonderful than we can imagine, and our job isn't to imagine it, but to look carefully and let it surprise us. So the next time you look up at the night sky, remember that out there, beyond the stars you can see, beyond even the galaxies, there are objects that defy the rules. Galaxies too old, stars too ancient, black holes too massive, structures too large, forces too hidden. Each one a reminder that the universe is still revealing itself, still showing us new things, still teaching us how much we don't know. And we're lucky, in a way, to be alive at this particular moment. The age of telescopes powerful enough to find these objects. The age of satellites and supercomputers and theoretical models, complex enough to know when something doesn't fit. The age when humans, brief and small as we are, can look out across billions of light years and find things that should not exist. Think about what that actually means. For most of human history, people looked up at the sky and saw lights, points of brightness against the darkness. They didn't know those lights were distant suns. They didn't know how far away they were. They didn't know that some were stars and some were galaxies, and some were even quasars from the early universe. They just saw lights, and they made up stories to explain them. Constellations, myths, astrology. The lights became characters in stories told around fires for thousands of years. We've come a long way. We've measured those lights. We know what most of them are. We can see things that no human eye can see directly. We can detect black holes through their effects on surrounding matter. We can map the cosmic web with surveys of millions of galaxies. We can study the cosmic microwave background, the afterglow of the Big Bang itself, and learn about the first moments of the universe. This is a very recent achievement. Most of the science we've used in this video was discovered or developed within the past 100 years. Some of it within the past decade. The Webb telescope is only a few years old. The understanding of dark energy is from the late 1990s. The discovery of the cosmic microwave background was in 1965. We're still in the early stages of figuring out what the universe really is. That means there's so much more to learn. The puzzles we've discussed tonight are just the ones we know about. There must be others we haven't found yet. Things hidden by distance, by the limits of our telescopes, by the angles at which we can observe them. The next generation of instruments will reveal more of these. The extremely large telescope, the square kilometer array, future space telescopes that haven't been built yet, each of them will push the boundaries further. Each will find new things that don't fit our models. That's not a problem. That's the point. Science isn't a fixed body of knowledge. It's a process. A way of discovering what's true by being willing to be wrong, by following evidence where it leads, by changing our minds when reality refuses to fit our expectations. These mysteries are exactly what science needs. They're the puzzles that drive progress. They're the questions that keep researchers awake at night, working to understand what they mean. And someday we will understand them. Maybe not all at once, maybe one at a time. With better measurements and clearer theories and new ideas that fit them all together. Maybe we'll find that some of them aren't really rule breakers after all. They're just signs that we were thinking about the universe wrong. We'll update our models. The unexplained will become the explained. Other mysteries will remain. New impossibilities will appear. The universe will keep showing us things we don't understand, and we'll keep working to understand them. That's how it goes. That's how we learn. For now, though, the universe is full of mysteries. Galaxies that grew too fast, stars that might be older than time, black holes that were born already massive, clusters too heavy for their age, walls and rings and arcs at scales that shouldn't be possible, forces hiding behind our own galaxy, pulling us toward unknown destinations, stars at the edge of stability, slowly puffing themselves out of existence. Black holes eating faster than physics says they should. The most massive single objects in the cosmos. All of them out there, all of them real, all of them waiting for us to figure out what they mean. The universe is bigger than us, older than us, stranger than us, and full of impossible objects. Sleep well. Out there, somewhere, beyond what we can see, more impossibilities are waiting. We'll find them eventually. And when we do, the universe will show us, once again, that it is more than we know. Good night.